And it is indeed recording. So this is the problem that I'm working on today. I'm going to bring it a little closer. There we go.
Sorry, where did you say it was? I'm looking through the chat. I don't see anything like that in the last 5 days.
Okay. It might have been a little bit longer ago.
It's also on the AP College classroom in our mechanics for one of our assignments.
Here we go. Oh, that's what I just sent. Here's a key. Okay, going back.
Find where he sent, where Giannis was sending in pictures of his questions. And earlier, Mr. Blessman sent in the testing guide.
Yeah,
it should be on Wednesday.
It's before that, actually.
What's the date of the when you
I'm looking. Just a minute. We'll get this. Here we go. I found it. Here's what I'm going to do. I'm going to just forward it to us. Oh, whoa.
What's the date?
Okay.
I think it's the 28th.
4/28.
Yeah,
It
28th.
is indeed the 28th of April. So if you look in the WhatsApp group, it's there. Okay. Yeah. Okay. So here's the problem. We have a gun-like device. Is my camera getting worse, or is it like dirty or something? It just seems like, does it not? Am I dreaming?
It already does seem pretty not good.
Maybe, let's see if I need more light, maybe. Is that what it is? Hang on a second.
It might just be your connection.
Lights, camera, action. There we go. Let's see. It's not very shady. I don't like that. Maybe that helps a little bit. I'm not sure. Okay.
Okay, can you show me again like the worksheet that you have in front of you right now?
Yeah. So I'm just hold it up one more time.
Is that the same one that you sent on April 28th?
It is. Yeah, there are two on April 28th. There's the actual scoring guidelines, and there's the actual questions here. But I'll redraw it either way, so don't worry. This is kind of like, not really very high tech here. We've got, that shows up nicely. Okay, so we have a length L shooting device of some kind, and it shoots some kind of bullet. Okay, here's the bullet that is being shot out. It has a mass M. It has an initial velocity of V. And then over here, it's got some kind of big block sitting over here of mass big M. Okay, that shows up nicely, right? Okay, so in here, they have a constant force F. Okay, and a dot of mass M in the horizontal direction as it moves through a tube of length L. After exiting the tube, the dart collides with a box of mass M that sits at rest on a table with coefficient of friction mu k. All right, so it's a table over here, and we have here a coefficient of friction mu k. The dart block system then slides across the table and comes to rest after traveling a distance d. So because we're out of space over here, we'll just assume that distance is relatively small and just say, okay, afterwards it slides over a certain distance d and stops. Okay? You guys understand the problem? Okay, I'll take that as a yes. Now, let's take a look. Students experiment with a variety of tubes, assuming that air resistance is negligible and that all other parts of the experiment remain the same. Should the students use a long tube or a short tube to make the stopping distance d the longest? Justify your answer. Wow, this seems a little bit too easy at this stage of the game, but maybe that's just me. Okay, so would L being long or short be more helpful in making this thing take a longer distance to stop? And just say, it seems silly to take time to write it down. Okay, you guys are being shy, I like that. So let's call on somebody. Let's ask, maybe not. Maybe I should ask somebody. No, I don't know. Adam, are you there? What do you think? Would a big distance L be helpful for making this thing slide further, or a short distance L? All right, not sure if Adam's actually there. So maybe we'll check down the list. Ethan, are you there? Okay, well, this is kind of making me feel lonely a little bit. Are there still people out there?
Yeah.
Yeah.
Okay, all right. Let's ask then, I think that was Rhea's voice just a second ago.
Yes.
So,
Well, it says that the force is, there's a constant force when it's in the tube, I believe. So
yeah,
I think the longest tube will have it because
sure,
force times distance would be work.
sure.
And then work is related to kinetic energy and thus velocity. And then we use momentum, the momentum equation.
Okay,
To determine,
good.
yeah.
So, big L would cause more work to be done because work is F times L, right? And then, of course, that would lead to more or a bigger V, right? And why is that the case? Because why does it cause more speed if you have more work done on an object?
Work is equal to delta K.
Right, the work done is equal to the change in kinetic energy. And of course, in this case, because we're starting from rest, work equals K delta K is equal to the final kinetic energy when it's leaving right there, right? Because initial kinetic energy is 0 when it starts over here. Right, it's starting from rest. And then, of course, K is equal to 1/2 mv squared. Whoa, I'm already off screen. That's pretty classy. Maybe this answer was actually more complicated than I thought. Okay. And of course, if the bullet's moving faster, it will cause a longer distance, right? And Rhea kind of pointed that out because the collision conserves. Okay, maybe again time to ask momentum, kinetic energy, or both. Okay, kind of a multiple choice. When that bullet embeds itself inside that block, does that collision conserve momentum, kinetic energy, or both? And maybe just, let's do this. Let's have you guys answer this by putting A, B, or C in the chat. Or I don't know, is that a good way of handling this? Maybe not. Maybe they'll keep you from
Zoom
cheating.
chat or WhatsApp?
I meant in the actual like chat in this conversation here. Is anybody using that actually? Let's see. Oh, there, Rhea did answer. Nice job, Rhea. You answered. Sammy answered. That's cool. I have proof to people being here. That's cool. And Lorelai's here. Octave's here. Cool. All right, good. So indeed, momentum is conserved. And can you guys explain to me how you know that momentum is conserved? If I asked you to confirm that, to verify, to justify why momentum is conserved, could you express that in words? And let's call on somebody else and let's maybe ask Lorelei, why is momentum conserved in this collision when this bullet embeds itself inside this block?
Wait a second.
Wait, was this a trick question? Because there's a force of friction, isn't there? Because of the mu k?
It's not a trick question, and there is a force of friction.
When you have an outside force on it, though, isn't momentum not conserved?
Ah, I see what you're saying. So you are correct. So technically, the collision between the bullet and the block, momentum isn't completely conserved, but we're going to make an assumption that it is conserved, similar to the momentum of one car crashing into another. The total momentum of the two cars right after the collision being the same. And here's the trick. Physicists would use the word right after the collision and t equals 0 seconds kind of interchangeably. And the key here is that when you look at the bullet striking this block and think about how much time that takes, or if a car hits another car, how much time that takes for one car to complete its collision with the second car. And I mean like just the crunchy part, the boom, that part. That time is long or effectively zero.
Zero.
It's zero, exactly.
Yeah.
So in this case, the bullet embeds itself in the block in a time that's about zero. So the forces that are acting on the block during the collision, technically, there is some friction on the surface that is resisting the block getting going in this case. And first it would be static friction, then it would be kinetic friction. But because the bullet embeds itself in this block so quickly that the time is maybe a millisecond or something very slow, like very short like that, then effectively the large force between the block and the bullet, that force is so much bigger than the friction force that we can ignore the external friction force during the embedding process and only during the embedding process.
Okay. Thank you. Okay. So then, okay, I stand by the first answer.
Yeah, it's a good answer, and it was a trick question, but yes, exactly. So we're getting exactly at the right key things here. So I'm glad we're doing this problem. Initially, I thought it was way too easy, but then I realized that I'm not taking the exam next Monday. It's you guys. So it's good we're reviewing this. So don't worry if you didn't quite remember all that stuff, but we're working our steps through. So I think it's good we're doing that. Okay, so then we come back to down here. We say, okay, well, indeed, the momentum is conserved, and it's conserved to specifically specify, that's redundant, to specify what's going on here. All the relevant forces are internal to the bullet block system, okay? And those are equal and opposite, according to Newton's third law. So the net force on the block bullet system is effectively zero, and therefore momentum is conserved. All right? Now, why is kinetic energy not conserved? Isn't just the bullet losing kinetic energy and transferring that loss of kinetic energy to the block?
Wouldn't the masses change though? Because you have mass 1 plus mass 2.
Well, I know, but the kinetic energy, the bullet had kinetic energy, right? 1/2 mv squared and little v squared, little m, little v. And then it's embedded in the block, and then afterwards they're moving together. Wouldn't just that big block bullet system have as much kinetic energy afterwards?
But the mass is changing from only the bullet mass to combined.
Sure, but still we could just say, the bullet had 27 megajoules of energy. I don't know what the number is. And then afterwards, the bullet block system has 27 megajoules of energy. Can that be?
Well, it's not a perfectly elastic collision. That's the
Okay,
words that I look for.
Sure,
but-
it's not elastic. That's true. So it's definitely not true because of that. But can you give me a physical explanation why this is not the case? Why in this situation is kinetic energy not conserved?
I mean, the formula for kinetic energy is mv squared, right? So
Mhm.
if the mass stays constant, but the velocity drops, the
Yeah.
overall kinetic energy also drops.
That's problematic because, so if we have this, second board. So here's what we had, mv, right? And then afterwards, and we'll call the speed afterwards big V. That's conservation momentum. That's true?
Yeah.
Yeah. Okay, that's right. But what we have here, you're right, V is going down compared to little v here because the first part is going up, right? M plus M is going up and big V is going down. True, but because this is going up, this going down, it can still be constant in terms of the product. So if we look at kinetic energy, though, here it's still true that M plus M is going up compared to little m, and big V is going down. So couldn't this still balance out?
Well, no, because if they're going up and down by the same by the same factor, then by the same amount, then the v squared would like
Awesome.
the squared
Okay.
that'll be like way more effective.
So you can have two explanations. So you can have a kind of a math explanation, right? And that's what Sam did just now. Sam basically said, mass, example, if mass increased by 2, like if the two masses were the same, right? Then it would be true that V goes down by a factor of 2, okay? And if that's the case, mass increasing by 2, V decreasing by 2 would mean because we're squaring V, that drop by a factor of a half of the velocity would drop by 4 the kinetic energy, and the increase in mass would only compensate for a factor of 2. So overall, the kinetic energy would decrease, okay? And that's a relatively complex explanation, but it's acceptable. But there's a better kind of qualitative explanation for the situation. And now just imagine as that a bullet embeds itself in that wood block, what slows the bullet down as it enters the block?
The force of the wood block.
The wood is
on the
acting on it,
wood.
and what kind of force is that when you have kind of, the bullet is kind of like a drill or like something that's kind to get into that wood, right? What kind of
Like a
force?
normal-
Was that?
Normal force? Or
Yeah,
Newton's third law force?
yeah.
Can
So
that just be friction?
it is friction. So if you kind of imagine you have a drill or something that is trying to get into this, and it's moving at a really high speed, okay? So it's getting a very large amount of friction. What would happen to the wood in this process?
Get hot.
It would get really hot, right? And if you have, for example, if you're drilling into a material, so say, for example, you're drilling into metal, you might be aware that sometimes processes in factories where they drill through metal, they have to cool that area because otherwise it overheats and the drill breaks and or the material breaks, or in this case, actually, it could actually put the wood on fire if you've got enough energy in that bullet, okay? So there's a lot of heat being freed or released in this process. And what does that tell us about the conservation of kinetic energy in this case?
It's not conserved.
It's not, because there's a release of energy into heat and sound. So there's loss of energy to those dispersed heat and sound areas. Make sense? Okay, so that brings us to the end of question A, and that was a lot more complicated than I expected. Wow. Okay, good. I'm glad we had this little conversation about that aspect, and we conserve momentum. And of course, that means if momentum is conserved, that means that then more L would cause more V. And then, of course, that would mean that that would cause D to get bigger, because at the end, again, we're doing work. Wow, this is actually a really complicated, if you actually work this all out and explaining this in words, this becomes kind of complicated. So a larger V will create a larger D, because a longer distance will be necessary at the end for friction to do the work to stop the block. Okay, which means then, of course, that friction force times D would have to be equal to that kinetic energy of the block. There we go. And that means that D has to be bigger. Okay, did I scare the children with that answer, or is that helpful? Or is it both, and then that's also good?
It's good.
It's good? I have class till 5 p.m., then I have a class actually after this. What do you need? Okay, good. So we answered question A. Ooh, wow, that's hard to see. Okay. Is this still good? Is it good we're doing this problem? I'm feeling a little bit lack of energy, but that just might be because we have lack of energy, which is okay. Are we doing the right thing here?
Yeah.
Yeah. He was like, we're all gonna die. This is gonna be hard. Okay. I just sent you guys my board work on WhatsApp. And let's get rid of this stuff over here. Good. So, okay, let's take a look. They have here a, my gosh, it's hard to read. What? Do you guys understand what they're saying?
No.
I don't know either.
I think I tried this problem and I was just really confused because there were like all the left and right and stuff.
Trying to
in the
code
equation
it.
does
Yeah,
not
you're
make
right.
sense.
FLM M plus M squared over mu kg.
PDF, it kind of messes up the equation. The same problem is on the AP Classroom.
Oh, okay. And Rhea, do you have it? Is it okay? I'm just going to see if this works. I think it says D is equal to, and then
FL small m
okay,
over in parentheses small m plus big M squared, close parentheses, coefficient mu times G, I think. Yeah, mu K, yeah.
Is that what they have?
Yep.
Cool, great. So this is what they've given you as an answer for this, and then they ask you to say answer the following. Without algebraic manipulation of equations, explain whether this equation accurately matches your explanation in part A. Whoa.
Well, as L increases, so does D,
Sure.
which is what we stated.
That's true. So if L goes up, D goes up. Makes sense. Is that all they're looking for? That seems kind of silly. Let's see what they got for their answer here. So part B. Oh, that's it. That's all they want. Okay, that's pretty straightforward. So yes, because as the length increases, because it's on top and then distance also increases, that means that this matches our prediction. Fine. Okay, let's take a look at question C. Students then change the force so that it can be described as a function of position, f of x equals 12x. Well, isn't that great? So now the force is no longer constant, but it's actually an increasing force as distance increases from the initial position. Okay, so basically now we're saying, hello, this force starts at a certain amount here. We're going to put our coordinate system in like this, right? And say that as we move along x, the force increases. Okay? That's the general idea. Explain how the students could use the equation given above to find the launch speed of the dart if the length of the tube is 2 meters. Okay, so another way of asking this question is, if I give you the function that tells you the force that something experiences, and I tell you that it starts from rest, right? That's the second piece. How would you use those two pieces of information? Okay, and then it also goes to a length of 2 meters. How would you use that information to find the speed of the object at the end of the process? And does somebody want to take a stab at this and suggest how you could use that?
Force is related to what's it? Potential energy. Can you do that equation? Like the integral?
Yeah, force is related to potential energy. And so yine, I would yine on this one. It is related to potential energy, but it's also related to kinetic energy. I think it's be easier to go directly to kinetic energy. Does that make sense? So I think where you're going to end up with is you're going to go here.
I don't want to say that.
W is equal to minus delta U. That's true. And in here is force, but it's also true that it's equal to delta K. And because we're trying to get at the speed, this is probably a more straightforward approach. Does that make sense, Rhea?
Yeah.
But in principle, you're right. The integral that you're taking can give you the potential energy or the change in potential energy. But let's go directly to finding the change in kinetic energy. That's going to be a little bit more straightforward. Okay, so that being said, so this one we're going to scratch. We're just going to say W is equal to delta K. And we're going to, this might be a good place to write that in here. To find work, right, we'd have to do the integral, right? And what integral are we doing? Maybe somebody else besides Rhea?
F dx.
F dx, exactly. So this would be F dx, and we've got to put the limits in here, like 0 and 2 are here, the limits, and you plug in the force, which is of course 12x, and then that's equal to delta K. And because it's starting from rest, that means that delta K is just equal to K, which is equal to 1/2 mv squared. Okay, so integral from 0 to 2, and then F, of course, in this case is 12x dx is equal to 1/2 mv squared. So our word answer, again, they're asking us to describe it, not to actually do it, would be to say, we're going to find the work by integrating the force, creating the integral of f dx from 0 to 2 meters, which is equal to the final kinetic energy, which allows us to find the speed because it's 1/2 mv squared or something like that. Make sense? Integral of force, limits, work, proportional to v squared. All good there. Okay. All right. So let's take a look at part D. So predict what will happen to the launch velocity of the dart if the length of the tube was doubled. Justify your answer. So taking a look at this thing here, what would happen if we were to double the launch velocity, double the length of the tube?
The distance would also double.
The distance would double, okay? So that means we have twice as long. So now the integral is going to change to 0 to 4, right? Up here, the limit is 4 rather than 2. Okay, so what would that do in terms of the launch velocity over here? What would happen over there? Okay, are you guys super insecure?
Well, wouldn't it also increase?
It would certainly
Yes.
increase, but let's think about how much it would increase. So we have 12x in here, right? Right? So when we integrate this, right? What will happen to the x here?
It'd be
Turn into an x squared.
X squared.
So 6x
So
squared.
that means if we're doubling the distance and the work done is proportional to x squared, that means doubling the distance will do what to the work done overall?
Quadruple.
Quadruple. So we have 4 times as much work. So doubling the distance would quadruple the work done. And if we quadruple the work done, that means we quadruple the kinetic energy that the arrow has when it leaves the little shotgun thingamajigger that we have there. And if the kinetic energy is quadrupled, what's true of V? By what factor must V increase in order for K to increase by 4?
A factor of 2.
Good. So here we go. So L goes up by 2, that means work goes up by 4. That means kinetic energy goes up by 4. That means that V goes up by 2. Okay, and that's kind of the written version here. You'd use words to describe that. Doubling the length of the tube will increase the work done in this case by a factor of 4, which would increase the kinetic energy by a factor of 4, and that in turn must be caused by the velocity being twice as large, because velocity squared is proportional to kinetic energy. Okay? Okay, you guys cool?
Yep.
Okay, now let's take a look at the last part, part E. Students are given an equation for the launch velocity of V equals square root of 12L squared over M. I'm gonna get this thing over here, maybe. Get that going for part E. So we have now a launch velocity of square root of 12L squared over M. 12L squared over M. They're giving that to us. Okay, fine. So without algebraic manipulation of equations, explain whether this equation accurately matches your explanation in part D. So, oh, yeah, wow, that's kind of a boomer move there. Okay, so here we go. So we're asking, does this equation match up with what we're saying? Well, they're kind of being a little bit sneaky here, right? Because Would we normally leave this like this? Leading question, vocal analysis says no. We won't leave that like this because it seems dumb to leave L squared in here, right? Okay, so we could rewrite this as L square root 12 over M. And now let's remind ourselves what we did in part D. We said if we double L, what happens to V?
Doubles.
Doubles. And this, of course, agrees because they have the same proportionality on the two sides. So indeed, for part E, we'd say yes. Yeah, V is proportional to L. Okay, so doubling L would double V, and it matches up with what we think should be happening. So it agrees. Okay. All right. Well, that's, you know, I thought initially that it was really easy, that problem, and sorry to make you kind of feel bad about, you know, your life and all that stuff at that point. But I think in the end, looking back at the problem, I think it was actually a pretty good problem. So we have we have work, we have momentum, we have kinetic energy, obviously, we have relationships between quantities, we have an area where you could be asked to not necessarily do an integral, but talk about doing an integral. So I think that's a pretty good question. So I think you should take a good look at that problem again. We finished doing it, but definitely put this on your list of, whoa, this might actually be relevant to what the actual exam looks like. Yeah, you guys agree?
Yeah.
Yeah. Okay, was that a sad yeah, Rhea?
No one else was answering.
Oh, okay. That's okay.
But yeah, I think it was a good problem.
Okay, it is a good problem, and it's actually a little harder than I thought. Initially, when I looked at the first problem, like, dude, of course, if you get a lot longer tube, that's going to make the block slide further. But actually, the explanation is the trick, right? And then actually, that's where the rubber hits the road. Which I think is also a good reminder to ourselves that even though it might be intuitively clear what happens, like if this gets bigger, that'll get bigger. Obviously, on the AP exam, they're going to want you to actually reason it out and explain clearly how you can justify that that is correct. So in just a reminder about the first part of the problem, that's really where a lot of the physics thinking was happening, talking about work done, kinetic energy, momentum transfer, and those kind of things. You have to really be careful about your language to make sure you hit all the points in order to get all the points, because most likely just saying, yes, so bigger tube will cause a longer sliding distance. They're probably not even going to give any points for that because it seems obvious, and it is obvious, but the explanation is where the rubber hits the road. Okay, that brings us to the end of that pack, and we are at 3:22. Okay, I'll take pictures of this and I'll post it in the chat. That's actually a good way of doing this, I think. And then maybe if I have to, I can always upload it later. So there we go. And here we go. And part E and there we go. Okay, that's that. And I posted that. Okay, good. So I hope you have last year's test, not necessarily on paper, but at least on your screen there. Okay, and if we take a look at that, let's see if we can figure something out in terms of what would make sense this year. The first question is an inclined plane with masses that are connected. This seems not necessarily a good problem for this year's AP exam, so I'm going to skip it. And I hope the next one makes more sense. If we're going to come back to it, we can, just as a review of things, but let's take a look. Okay, calculate the speed. So in part B, we have a acceleration that's time dependent. Ooh, that sounds like fun. And then in part C, we have the rotational inertia of a rolling object may be written in terms of yada, 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 daddle, daddle, daddle. Okay. Oh, this is good. I like this because it's got rotation. So we're going to maybe spend some time now looking at question 3. Okay. So here's question 3. I'm holding it up for a minute. And we've seen that kind of setup before, where we kind of got like a Hot Wheels setup with a long track and then a loopy loop. And in this case, we're not rolling a car down the hill and making it go around the loop. Here, we're making some kind of sphere or ring or something roll down and then make it through that circle and then go out the other side. Okay, that's the basic idea behind problem 3. That's where we are now. So we're in 2019. This is set 2. Set 2, and we're going to look at question 3. Okay, and again, all the questions obviously are good for learning physics, but we're just selecting ones that make sense in terms of what the exam is going to look like. And I think this one is probably the best one from the set, so let's take a look. So they have this thing go down, then they're going to have this go like this, and then they kind of go like that. Okay, and they actually go a little lower than that. There we go. And they have up here, this thing starts going there. There we go. This has a distance r. This is point A up here. And we got this at point P up here. And we got this from a height h. There we go. The rotational inertia of a rolling object may be written in terms of its mass m and the radius r as I equals bmr squared. Okay, so they're saying this rolling thing has a rotational moment of inertia of b times m times r squared. Okay, so what this is expressing is, of course, that the bigger the object is, the bigger the moment of inertia, and it goes as the square of the distance. Because just as a reminder, for a point mass, right, the moment of inertia is simply mr squared. Okay, so for a point mass, the factor b would be just 1. Okay, and for other objects, it will be smaller than 1. Okay, because you can't, for a point mass and other objects that have all the mass a distance r away from the center of rotation, it would be just mr squared, but everything else is closer. It might be 3/5 mr squared, 1/2 mr squared, and so on. Okay, does that make sense? So b is always going to be smaller or equal to 1. Okay, just saying that's how they're expressing it here. And we have a table in the book that you guys can look up to find it, for example. And there we go. So students wish to conduct an experiment to determine the value for B for a particular partially hollowed sphere. Okay. The students use a looped track of radius r, which is much bigger than the radius of the rolling thingamajigger. As shown in the figure above, the sphere is released from rest at height h above the floor and rolls around the loop. Derive an expression for the minimum speed of the sphere's center of mass that will allow the sphere to just pass point A without losing contact with the track. Express your answer in terms of B, M, R, and fundamental constants as appropriate. Now, let's kind of rephrase this a little bit for the AP exam that you guys will be taking on Monday, because that sounds a little bit complicated. But let's think about this, the ball as it comes through here, it comes around that way, and it's moving in this direction. And let's decode the language they're using. They're saying, they're asking for the minimum speed that it has to have in order to just pass point A without losing contact. So now let's rephrase that and say, if you were to solve this, how would you do that? Can you describe your problem solution process to part A rather than actually doing it? Okay, so where do we start? This thing just makes it around here without losing contact. Coded in there is the important statement for us. What is the important statement for us in there?
Height of 2r?
Oh, that's in there as well, but how about the without losing contact? Just making it around without losing contact. What does that indicate to us about the forces acting on the mass as it comes through around here?
That be the normal force would be, wait. Well, because like the forces would have to equal out.
So the net force is 0, is that what you're saying?
The net vertical force is 0, yes.
Okay, good. That's wrong. And that's I was kind of grimacing about, because I was afraid you're going to say that, or like anticipating you were going to say that.
Is normal force equal 0?
Normal force is equal to 0, exactly.
Okay, then there's still a force of gravity down, right?
Yes, it is. So we made the free body diagram at that point. Sorry, I had to make sure my power cord had come unplugged for some reason. And are we charging now? Yes, we are. Okay, good. So, so indeed, it's true that at this point, anytime they say just without losing contact, the amount of contact between an object and the surface has to do with the normal force. So if I put this pen on here, for example, and now I'm going to pick it up, and just as I start lifting it, the normal force my hand is providing gets smaller, smaller, smaller until my bottom hand. And eventually I lift it off. And when I lift it off, just before it loses contact, the normal force has become 0. Okay? So that means that at this point, this is the free body diagram. Fg is the only force that is acting. And if we're going to express this in words, we would say, just before losing contact, the normal force has become 0, and therefore the net force on the ball is equal to mg. Okay, that's the starting point of the conversation. Now they want us to relate that to the speed. In order to relate that to the speed, we need to go from the force now and make a connection with that. What is the thing that links the net force?
It's equal to mass times centripetal acceleration, so v squared over r.
Yep. So that is the force, and this is the only force. That means that at this point, net force equals mg, and of course that's equal to ma. Now, what kind of acceleration are we experiencing at that point? Is it direction changing, speed changing, or both?
Both.
Okay, both would not be correct.
Right.
And the reason for that is that it's only, let me just try to phrase that and help you out and see that. As it's going up here, is it getting fast? Is it speeding up or slowing down?
Slowing down.
Slowing down. And once it passes this point, is it speeding up or slowing down?
Speeding up.
Speeding up. So this whole time it's slowing down. After that, it's speeding up. So right at this point, it's neither speeding up nor slowing down. Okay? And that's good because the force we have is perpendicular to the motion. And a force that is perpendicular to the motion, the velocity of an object, so when you have v in this direction and f in this direction, you always have how much work being done on an object?
0.
0. So in order to speed it up, you'd have to have a force that pushes forward in the direction of motion. To slow it down, you'd have to push against the direction of motion. And the sideways perpendicular force will always do no work, therefore not change kinetic energy, therefore neither speed up nor slow down. So this is just direction changing in terms of the acceleration. So if we can put a little c on there over there on the corner. So mg equals mac. There we go. Oh, I don't like the little g. It looks like it's a subscript. It's not. There we go. That's better. Good. We can maybe tilt this. My gosh. You know, I tried to get a webcam on Amazon. They're like all sold out. Like a YouTuber cam, you know? Anyway, that would have been helpful. Anyway.
Wait, hold on, I have a question about the question.
Yeah.
Is it asking for the minimum speed at point A or the minimum like initial?
They're asking for the minimum speed at part A. In this part, they're asking for just that.
Okay, I understand.
Okay, and we're just kind of walking our way through. Now, up here, we're releasing it from rest. Normally, we then make a connection from this to figure out how high we have to start this process to make it work. Okay, all right. Okay, so let's take a look. We've got G equals AC. So just to word it out again, we said almost losing contact means the normal force is 0. Therefore, the force of gravity is the only force acting on the object and is therefore the net force. The net force is equal to ma according to Newton's second law. Because this object is neither speeding up nor slowing down, the only acceleration this experiences is a centripetal acceleration, and therefore we can substitute v squared over r for AC, and then we could solve for v. And if we were to actually write it out like that, right? Sorry, big R, because of the way this is set up. Good. And then, of course, that would mean that if you were to do this problem, it'd be the square root of GR would be the correct answer. There we go. Okay? Question?
I feel like I've seen that equation before. Does that apply like in most cases when we have a loop and normal?
This always applies in this situation. So it's going to be the same situation. That's correct. So,
okay.
So the rotation doesn't really matter here. The B is a little bit of a, what's it called? Like a distraction? I'm not sure. I want to say like a wild turkey, but that's not right at all. Anyway, it's a Fallstrecke here with the B. They tell you express your answer in terms of B, M, and R, and B and M both don't matter. The only thing that matters is big R and G. So, okay, and let's keep moving. And let's actually make sure that we got the right answer, by the way. That would be embarrassing if it wasn't right. Yay, it's correct. Good. All right. Part B. Suppose the sphere is released from rest at point P and rolls without slipping. Derive an equation for the minimum release height h that will allow the sphere to pass point A without losing contact with the track. Express your answer in terms of B, M, R, and fundamental constants as appropriate. Okay, so we're basically asking, now we're going to make this thing start from rest up here, right? So V0 equals 0, and we want to get to this point. Okay, now we're not actually going to do it on the test on Monday, but we might be asked to talk about it. So let's practice that a little bit. So we've got our object over here that starts from rest. It'll speed up. It's spinning. It goes around this loop. And then here it's just going to make it around because we started it from the minimum height to not make it not slip up here and fall off. And then it comes back around and goes this way. All right. So what approach would you use to connect this point up here to this point over there, if we call this point 1 or point 0? So this is t equals 0. And this is time t later. Okay, so how do you connect these two situations? This is point 1, this is situation point 2. How are they connected?
Conservation of energy.
Conservation of energy is the best way to do this, absolutely. So what kind of energy do we have at situation 1?
Potential energy.
Potential energy. So situation 1, we have only UG. Now, how about situation 2? What kind of energies do we have at situation 2?
Both. kinetic and potential.
Okay, so you could think, let's have UG2 and let's have kinetic energy, but I like the idea of not having not having gravitational potential energy. Can we make that happen? Hint, yes, because you figured that out by my vocal analysis that that's the case. You guys are so good at reading my voice. Okie dokie. If we want this to be 0 potential energy, we have to call this, not H, but call this H equals 0, or Y equals 0. Okay, let's do that. Y equals 0. That makes sense? So we're going to call this randomly 0 height. Then this object here would have 0 gravitational potential energy. Does that make sense?
Yes.
Okay, that makes it a little easier, I think, to look at. And of course, that means that at the starting point up here, Y, the height that this thing is up, is actually H minus 2R. Wow, that is super small work, and I don't even know if I'm on the screen anymore. So let's scooch it up just a little bit. There we go. So H minus 2R is the position up here. Okay, good. And now there's a second trap that's been set for you by the question writer, because you said kinetic energy, and you know, technically that's correct, but the simple reading of that would be, I don't think you're quite right that it's kinetic energy if you don't specify more clearly. What am I referring to?
Rotational kinetic energy?
Exactly. So it has rotational kinetic energy and linear kinetic energy. It has both. Okay, so you need to write them really both down because they have two different equations. That make sense? Okay, I'll pretend you said yes. Was that too simple or too hard, or just you're tired? Okay, I'll pretend you answered my question. So we'll just move on, and we'll write down the initial potential energy, okay, which would be M G H minus 2R, right? Correct? And that would be equal to linear kinetic energy. Well, that would be just 1/2 mv squared. And then the rotational kinetic energy would be 1/2 I omega squared. Okay. Focus. Focus. I'm not sure if I'm not talking about you, I'm talking to the camera. Although it'd be good for you guys to focus too, but there's a light out over here. What? There we go. That's a little bit better? No, I don't know. All right, I'll take a picture afterwards. Okay, so we were going to describe this in words. Just a reminder what the question was. They asked, find the minimum release height. So we're trying to solve for this, H. Okay, so in this case, how would we describe this? We would say energy is conserved in this process because it is a conservative force. Gravity is acting, and normal force doesn't interact here either. There are no losses to friction. So we would set the gravitational potential energy at the beginning of the process equal to rotation, the sum of the rotational and linear kinetic energies, and then solve for H in order to find that minimum height in order for this process to work. Okay? And if we were to go through the process, we'd relate omega to V. And just a reminder, omega is equal to V divided by the radius of the sphere. That's the connecting property between rotational velocity or angular velocity for something and its linear velocity. So they're related like that. Omega is V over R, and we can make that connection there. Okay? I feel like I'm hurting you people because you're so quiet. And
You're good.
We're good? This is good stuff? Are you just little sad that this is all a lot of stuff to know. Could you use a pep talk? I can do a pep talk. Should I do a pep talk? We can do a pep talk really quick. Just hang in there. Everybody's in the same situation, or even worse, I think. I think, relatively speaking, we're doing as much or more than the average school is doing. You're doing as much or more as the average AP Physics student right now. So I'm pretty confident on that. And I feel every time you do something, you work, you attend this Zoom session, or you do some problems, you're gaining one more little, chit to make this thing happen and work out and get you just a little bit ahead, and just keep your chin up, and you guys can do this. Go team. Was that inspirational? A little bit?
That was beautiful. Thank
That was
you.
very, very inspirational.
Oh, thank you. Thank you. I've been dreaming of giving that locker room speech to my AP Physics class, as weird as that is. Yeah, okay, good. So not exactly like a basketball team, but close enough. Okay, so we're through part B. And let's take a look at part C. They're going to ask us to do a graph. Now, we will not do a graph, and actually, but I think there's a good chance, and just a warning about that, that there might be a situation where they give you a graph. So instead of asking you to graph it, they'll complete the graph for you, given on the data points. I did that on question 1, and I totally sank your battleship. So just be prepared. I think that is a realistic assumption that might happen. They will not ask you to graph, but they could show you the graph and give you the slope and the y-intercept and ask you to interpret it. So that being said, let's take a look at the solution key and see the graph that they'd come up with in that situation. So they come up with a graph that has a y-intercept of 1 and a slope of 0.2. And I'm just going to hold that up for you. There we go. Here's the graph, and as you can see, the y-axis over here starts as 1 and goes up to 1.2, and the x-axis goes over from 0 to 1. Okay, good. So there we go. Plot the release height h as a function of b. Determine the minimum release height h for various other objects of radius r and known values of b. So what they come up with the more I think about it, the more I like the problem. And then probably the more you don't like the problem, the more I like it. That's not good, but that's just the way it is. I'll just draw you this drawing. So this is the graph they have of the minimum release height necessary to make it around the loop. Okay? So looking at this, where on this graph would a ring be located? A loop, a hoop, okay? A hoop like this that has all its mass at its edge. Okay, you guys understand that? Where would that be located on this graph?
Equals 1.
What, B equals 1 here?
Yeah.
Okay, good. So that means that a hoop would require the largest distance possible. Does that make sense?
Mm-hmm.
And why would that make sense, Sam?
Because you said it before.
I like it. So why would you need a very large distance to make this thing, make it around that loop? It sounds like super efficient. I just feel awesome about this ring. I feel we should be able to do it with a smaller height. I'm confused. Can you explain it to me, Sam?
Hold on. Is it still the same problem as before?
It is the same problem. We're saying we're kind of trying to make it around that loop, right? We're making it around that loop. Whoa. We're trying to make it around this loop, okay? And we're saying for a hoop, we need a bigger height than for a sphere, okay? That's what you're saying, okay? And I'm not saying that's wrong. And hint, you're actually right. It does require a larger height to make it around. But why? Because I just feel it's so efficient. We're putting all that mass on the edge, and that's like way better than a sphere, right? A sphere would be maybe here somewhere in there, and this guy would be up here. But dude, that seems inefficient. Why do we need so much height to make it around the loop with that hoop?
Crouch and interact to like
Because what?
No, sorry, my brother's talking at the same time.
Oh, it's your brother. Okay. All right. Samuel, you got an idea?
Well, is the mass still the same?
Mass is still the same.
Oh wait, because the weight is distributed to the outside, so that the rotational inertia is bigger.
Good. The rotational inertia is bigger. Therefore, it will have more of its energy stored in kinetic rotational energy, rotational kinetic energy, and have less energy over to make this thing move linearly. Reminder, in part A, we found the minimum, like the minimum speed required, a linear speed. And to get to that speed, we need to put energy into that. But as we have for a hoop, more energy is necessary to make it go at a certain speed, because at the same speed, this object has a higher proportion of rotational kinetic energy. Therefore, that would go here. Okay? That's the correct answer. So nicely done. And we are now at the end. That was kind of painful, but I think it's important that we keep working on this. We do have class tomorrow, and not to scare you people, but we have one more class tomorrow, Tuesday. And then we have a class on Thursday, one period. And then the second period of that class is going to be our mock AP exam. And that's it. And then on Monday also, we can kind of review a little bit before the AP on that day, May 11th, but otherwise we're going quickly towards the exam. Keep working. You guys can do this. I believe in you. You've worked hard, most of you, all year, and you know, keep it going, and don't lose track of the prize. You're almost there. Hope that was inspirational. I'm going to stop the tape now.